expecting to see 9.6 gigawatt hours of electricity produced every year.
The purpose of this shaft, it's the retrieval shaft for the tunnel boring machine is launched from the south shaft on the other side of the Fraser River.
We go out to 5 different sites. 3 of them are accessed by helicopter, 2 by ground.
Hello and welcome to the Sustainable Region. I'm Vanessa Timmer, and today we're talking about our region's drinking water system. The building you see behind me is the brand new Barnstone pump station, which sits just west of the Pitt Meadows and Maple Ridge border. This multi-year project is nearing completion, and when it goes into operation, it will deliver high-quality drinking water.
This piece of the Ridgewater Utility Project, including the new Barnstone Maple Ridge pump station, has been literally years in the making. Putting the roof on the building was a major milestone.
We're getting into the stage of just starting to put the roof on. Today they're actually swinging the roof beams into place. The beams here are made of wood. They didn't need to be made of wood. They could have been steel, but we felt that this was an interesting architectural feature. It also uses a resource that is sustainable. These are glulam beams. They're made of layers of wood or planks that have been glued together, and they're obviously protected with a colored coating as well, so that they will last for a very long time. The glulam beams are being moved into place with this crane that is also used for bringing in other heavy objects into the site. But once the roof is on and complete, from the outside it might look like the building is fairly finished. We then have a lot of work to do inside.
Okay, coming down. Yep. Fingers out of the way.
We have to install all the wiring and pumps and the control systems that run them.
Moving the pumps into place and installing the other infrastructure in the new building is a slow-moving and difficult task. Each piece needs to be precisely placed.
There's going to be 6 pumps initially. 2 pumps to Maple Ridge, 3 to Langley and South Surrey, and there'll be 1 spare. And then on either side of those, there's a bypass. 1 bypass goes down to Langley and South Surrey, 1 goes to Maple Ridge. So the water will flow through the pipes coming from Coquitlam, through the pump station, and then out again. As the demand increases in other parts of the year, the pumps will be used more and more. The other 2 pumps are only sort of scheduled to be installed in about 30 years' time, so the 6 pumps will be sufficient until then.
For people that live next to the pump station, the wall right now is a big concrete object, and it's not very nice to look at. But when the building is complete, the overhang of the roof, you can see on the beams behind that they do extend beyond the edge of the wall here. They'll be able to see the surface of the green roof, or a roof that is planted with plant material and grasses, and it'll partly block the view of the wall.
I would say we tried to anticipate all the neighbors' concerns as much as possible. Many of them were surprised that the building actually, to some extent, had any design thought at all. Our standards for these kinds of industrial buildings have been historically not very ambitious. We felt it was important that the building have a little bit of a face toward low heat, that the building have a sense of quality overall, as opposed to just looking like another Glock building.
The wall is designed so that the noise that comes from low heat highway towards the residence and was once screened by some trees that were on this site will actually be blocked by the building. The green roof is designed to absorb water that would fall on the site. So it'll contain rainwater, but it also deadens sound and stops it reflecting back into the neighborhood.
These are public facilities that are important to all of us. We all use water. And often they're kind of hidden away, and because the region is densifying, the kind of easy sites to stick them away from sight, they're not that easy to access anymore. So we have to have more of these facilities in denser areas. So the way we choose to design them to make them fit properly into dense areas, be an aesthetic benefit, and also respond specifically to the urban design needs of a neighborhood is a really important challenge.
Neighbors report they are pleased with how the design is turning out, as the building does block their view of traffic on low-heat highway, as well as the noise, and it offers privacy. The pump station is now in the final stages of becoming operational by the peak days of summer in 2015.
Welcome back to the Sustainable Region. The equipment in this pump station is only a fraction of what Metro Vancouver operates 24/7 each day of the year. It's all part of our regional government's commitment to delivering the best drinking water possible, building, operating, and maintaining one of the largest water systems in North America. Our region's geography makes this a complex task, having to pipe drinking water under the Fraser River, for example. Right now, Metro Vancouver is constructing a new water supply main downstream of the Port Mann Bridge, more than doubling the capacity of the existing main. Here's an update on that project.
Metro Vancouver is constructing a new water supply main under the Fraser River, downstream of the new Port Mann Bridge. The water main will be constructed in a 3.5-meter diameter tunnel deep underneath the riverbed. A specialized tunnel boring machine, or TBM, digs the tunnel and also assembles the concrete tunnel liner protecting the steel inner pipe. Once complete, the water main will carry clean drinking water from the Coquitlam Reservoir to communities south of the Fraser River. The TBM started its journey on the south side of the river in Surrey and is now headed to Maccabee Park in Coquitlam on the north side of the Fraser River. As the tunnel boring machine works its way under the Fraser, crews at the north side job site prepare for its arrival with the construction of a vertical shaft connecting the north end of the tunnel to the surface.
The purpose of this shaft, it's the retrieval shaft for the TBM. So the tunnel boring machine is launched from the south shaft on the other side of the Fraser River. So once the TBM breaks through on this side, the TBM equipment is hoisted out of this shaft.
The first step was excavating for the shaft.
To begin, we had to install slurry walls, which provides temporary shoring support until you can get concrete in these panels. And you do that until you have a full circle, and then you excavate out the middle of the shaft using a clamshell bucket and a crane. And then you can build the permanent lining inside of that.
With the slurry walls built and the shaft excavated, crews are now constructing the permanent liner for the north shaft.
Slurry walls are 81 meters deep. The shaft itself, which goes to the top of the tremie slab, which is the plug at the base of the shaft, that is 63 meters deep. The inside diameter after the permanent lining has been placed is 5 meters.
The cages are lowered into the shaft where they are encased in a special concrete mixture.
Because the concrete is so strong and the walls are so thick, we have to cool the concrete with water cooling pipes just to keep the heat of hydration down and prevent the concrete from cracking. So the rebar cages are assembled on the surface, and then the cages are lowered into the shaft, and then the concrete is poured.
A large hopper transports the concrete down the shaft to the work area, where crews pour the concrete through an opening in the form. To protect the shaft during seismic events, a layer of high-tech plastic fabric provides separation between the slurry walls and the concrete shaft.
Well, this shaft is quite unique in the sense that because it's so deep, the behavior of this shaft under a seismic event is much different than the shaft on the other side of the river. So we actually had to isolate. The design requires that isolation layer between the slurry walls and the permanent lining. So that gray fabric you saw, it's called UHMW, which is ultra high molecular weight. Essentially it's a plastic, and it provides a slippery separation layer between the slurry walls and the permanent lining. You do not want the slurry wall to grab on to the permanent lining because it increases the seismic loading on the permanent lining structure.
The north shaft will also serve a purpose once the TBM is removed from the tunnel.
So once the TBM breaks through on this side, the TBM equipment is hoisted out of this shaft. And then essentially what happens after that is there's a valve chamber constructed on the surface, and it controls the flow from the Coquitlam water to the other side of the river.
The scheduled completion date of the Port Mann Water Supply Tunnel is spring 2016. We all love food.
What's not to love?
Until we're done with it.
Hey!
Then food scraps end up in our garbage.
What? Food isn't garbage!
Yeah, not garbage!
40% of what we throw away is food, but now food scraps have somewhere better to go.
Put us in your green bin!
Yeah, green bin!
Food scraps can be turned into compost, and that's good for everyone.
Yeah!
Put your food scraps in your green bin so they can be composted. Food isn't garbage.
Not garbage.
Welcome back to the Sustainable Region. The equipment here is worth more than $10 million, but the largest water infrastructure investment in the region is the Seymour Capilano Water Utility Project. which includes the new Seymour water filtration plant and the installation of twin tunnels running underground across the North Shore. Because the filtration plant is at a higher elevation than the Capilano reservoir, excess pressure builds when the treated water is returned downhill through the tunnel. And this creates the possibility to actually generate electricity using an energy recovery facility and a giant turbine.
Moving 12 tons of solid steel may sound like a job for brute force, but it is actually a delicate business. Getting this big blue turbine inside this small gray building will require 2 cranes, lots of planning, specialized lifting gear, assorted cutting tools, and some elbow grease.
This piece of equipment is one of the heaviest pieces. It weighs a little bit less than 12 tons, which is our ultimate capacity of the inside crane. To put it in and place it, we are actually going to use 2 cranes and spin it until we place it.
The turbine is being installed as part of Metro Vancouver's Seymour Capilano water utility project, providing cost savings by harvesting the energy available from the water returning to the Capilano reservoir from the Seymour Capilano filtration plant. Because the Seymour Capilano filtration plant is higher in elevation than the Capilano reservoir, excess pressure will be generated when treated water is returned to Capilano for distribution. This water pressure will spin the turbine, generating electricity that can partially offset the power requirements of the pump station.
The power of the generator is almost 1.7 megawatts, and according to the flows that we've seen historically, we're expecting to see 9.6 gigawatt hours of electricity produced every year.
9.6 gigawatt hours of energy is roughly the same amount of electricity that 1,000 homes would consume in a year.
It can cover the consumption for heating, electricity, and other base consumption of both Capilano pump station and energy recovery facility, or it can cover a bit more than what one pump uses down at the Capilano pump station.
But first, this 12-ton piece of custom-built equipment must be moved into its permanent home. While one operator controls the crane's movements, another worker, called the slinger, directs, watching carefully as the big box containing the turbine is moved from the truck and lowered into position for its final move into the building. The turbine is lowered onto a set of steel skates. These wheeled plates support the box and allow it to roll along the beams put in place to bridge the opening in the wall. 2 cranes are required for the final stage: the truck crane outside and an overhead crane inside the building. It's a delicate operation with no room for error. Finally, the turbine is lowered into its final position and bolted into place.
Once all the pieces are installed, we are going to do dry commissioning. After that, we're probably going to use 1 or 2 pumps from the pump station to do partial wet commissioning. And then once the treated water tunnel is in service, we are planning to do a full commissioning.
The project is scheduled for completion by mid-2015. Metro Vancouver's award-winning video series highlights topics you may not consider when you think about living in our region. How do you bore a water tunnel under Grouse Mountain? Why is eating fiber linked to generating electricity? Can you use light to disinfect drinking water? Plus, you'll never guess what we found in your garbage. Clean air, safe drinking water, waste reduction, and more. Get behind the scenes for the major projects, cutting-edge science, and innovative solutions that sustain our livable region.
Welcome back to the Sustainable Region and our look at Metro Vancouver's water system. You may be asking, where does all the water running through these pipes and eventually flowing out of your taps come from? Well, we can thank our 3 watersheds for that. 585 square kilometers of mountainous lands that are closed to the public. This is to protect the lakes that supply our reservoirs. These lakes collect water from creeks and streams and also from melting snowpack. Metro Vancouver staff carefully monitor the depth of the snow in the stunning scenery high above our region.
It's something most Lower Mainlanders never get to see, but for Metro Vancouver's watershed protection staff, it's part of their regular duties. They travel by helicopter into the remote wilderness behind the North Shore Mountains 8 times a year in winter and spring in order to measure the snowpack.
We go out to 5 different sites. 3 of them are accessed by helicopter, 2 by ground, so we hike into those. All right, so we are at site number 8. We collect a series of data to get snowpack depth.
Course 302.
That information is also passed along to River Forecast province, and they use that data in terms of stored water and also for the spring flooding.
When the crew lands, they assemble a long pipe which is then driven into the snow. It's measured and weighed.
We'll take the empty weight versus the weight with the snow core, and then from there we can work out how much stored water is in that given parcel of snow, and then over the series of sites that we do, we get an average.
The amount of water being stored as snow is important because if the snowpack melts slowly, it helps keep our reservoirs full during the dry months of summer. But if it melts too fast, it can also be a threat, creating the potential for flooding.
Yeah, so directly below us is Disappointment Lake. It's one of the more northern points we have in the Capilano watershed.
The history of how the lake earned its name has long since been lost. Disappointment Lake is one of the oldest snowpack testing sites, offering decades of scientific data, with an amazing view.
It actually puts it better in perspective to me when I bring people here, because they remind me of that. You kind of get used to it, but it is good to keep that in check.
The snowpack varies widely. In 1999, it was more than 9 meters, burying this entire weather station. But 2014's measurements were less dramatic.
We're seeing about 80% of historical normal. There's no significant concern. It's not too low, but it would be definitely on the lower side.
Snowpack measuring starts at the end of December every year through to the end of June.
Well, that's it for today's show. Thanks for watching. You can view, comment on, and share these stories and more on our blog at metrovancouvervideos.org. For the Sustainable Region, I'm Vanessa Timmer. See you next time.